Welcome to Sundar's lecture. This is lecture number 45, and in this lecture we are going to see series RLC circuit now, AC through series RLC circuit. So this is the title, AC through series RLC circuit. And what are all the topics we have seen in the previous class? See, we have taken two problems, right, related to series RC circuit, and we have found what is the real power, reactive power, and apparent power with the power factor. And then in this problem, we have found what is the real power and how this pi value looks like. Right? In the problem number 1, we have taken that the reference voltage is not at 0 degree with a minus 90 degree, and we have seen many things in this problem. Right? So in this class, we will take AC through series RLC circuit, right? We have started with only R and L, C, then we have seen RL, RC. Now we have entered into the final one, that is series RLC circuit, right? An AC source is connected, V is equal to Vm sin omega t, that is connected to a resistor, inductor and capacitor that is connected in series, right? Now we know these kind of things and all. We have already seen, right? What is the voltage across this resistor R, that is VR, which is equal to I into R. And what is the voltage across inductor, that is VL, which is equal to I into XL. And what is the voltage across C, that is VC is equal to I into XC. And we know these phasor diagrams, V and R, V and I, VR and I will be in phase if it is a resistor. And if it is an inductor, then VL will leads the current by 90 degree. Try to understand, I am saying with reference to current. And then C, that is under capacitor, the voltage, that is VC, lags the current by 90 degree. All these kind of things and all we have seen already, right? What is the total voltage? That is also we know. The total voltage, that means V, that means I am writing this this in phasors, which means V phasor will be is equal to VR plus VL plus VC. So this is the voltage phasor in this one. But in series circuit, I will be the common one, that is the fixed one through all the components. Now what we will do, see here we have to go for 3 cases. First case, maybe I will write it down. Case number 1. In the first case, what I will take, let be XL is greater than XC. So we know what is VL. So maybe I will take a different color. So you see, what is VL? VL will be is equal to I into XL, and what is VC? VC will be is equal to I into XC, which means you see here, if XL, let we consider that XL is greater than XC. So if XL is greater than XC, then obviously with this expressions we can directly write VL is greater than VC. VL is greater than VC, which means we have an amplitude of voltage across this inductor is greater than the amplitude across the capacitor, amplitude of the voltage across the capacitor. That is the difference we have to take here. So now we try to draw the phasor diagram. So how will you draw phasor diagram? We have seen these things anyhow, we will do now. So phasor diagram. So what I will do, I will take I as the reference now. So we will do this one right through. We have taken in all the cases, I will be the reference phasor, right? This I will write it as I. I phasor. Now what happens to the VR? Obviously VR will be here. Obviously VR will be here, because that is in phase with I. Now I will take VL in this direction, maybe see, this is now VL. VL always leads, right? VL always leads the current by 90 degree, and VC will lags the current by 90 degree. So I will take like this. So what is this one now? This is nothing but VL, right? This is nothing but VC, and this angle will be 90 degree. Maybe I don't need to write this one. You know this one, right? So always VL leads the current by 90 degree and VC lags the current by 90 degree. And what we have done here, see VL is greater than VC. Then obviously what happens to this one now, this voltage phasor will lies here. Since VL is greater than VC, we will write it as VL minus VC. If you take amplitude difference, then it will be leading the current phasor by 90 degree. Right? So now what happens to this one? So this one to be connected with this one. That means you see this one and this one should be connected, right? So what is this one now? Simply we can say that this is the total V, right or wrong? Since this is the voltage across this circuit, right? What is this one? This total, this one we can say it as V. So in phasors, if you want to write it down with respect to the Pythagoras theorem, what we can write here, V, that is total V will be is equal to square root of, what is this one? This one will be VL, this one will be VR. So VR square plus what we can write, VL minus VCD whole square. That's all, right? Or this value, this one will be also what? Will be also what? VL minus VC. We know these kind of things we have already seen. So this is nothing but VL minus VC. So this is the voltage expression we have found now. So now what we can do, we just try to get the impedance value. How will you get impedance value? This one, what we can write it down, this can be written as I into R the whole square plus, and in this one we can write it as, this will be I into XL, what we can do, this is square minus R, it can be whole square, right? So it can be written as I XL minus I XC the whole square, right? So this is the formula. And what we can do, we can take I commonly outside, so that I can write it like this. This will be is equal to R square plus XL minus XC the whole square. We can write like this. And what is this one? We will write V will be is equal to I into Z. So commonly we can now write Z will be is equal to square root of R square plus XL minus XC the whole square. And this Z is comes under which case? Is comes under XL minus X. XL is greater than XC. So this is the formula. This is the formula for Z impedance under the case where XL greater than XC. Now what we will do, we will take the case number 2, that is XC greater than XL. For that we will go to the new page. So case number 2 now. This is case number 2. Case number 2, which means what we will do, XC is greater than XL. We will do like this. So obviously from this one we can directly write that VC is greater than VL. We know this one from the previous case. We can write like this. And what we can do now, we will draw the phasor diagram again. So phasor diagram. So in phasor diagram, again we have to take the same things. What we can do, see, this is the reference phasor, that is I, we know this one, and this is the VL phasor, that is the voltage across inductor, and this is the VC phasor, that is the voltage across the capacitor, right? So we will write it down anyhow. So this is the reference phasor I. So obviously what happens here, this will be VR, we know this one, and this is VL and this is VC. Now in this case number 2, VC is greater than VL. So obviously what happens now? So it will be here under this one. So this is VC minus VL, right? Now what we can do, we can connect these 2 points. That means this one and this one we can easily connect, and this is nothing but now the value of V. So we can write this is the value of V, right? This is the value of V. Now you see, and what is the angle? Angle, you know this one. Angle between, what is the pi? V, the angle between V and I. Obviously, this is the pi value. That also you have to know. That you should know. See this one here also. This is the I and this is the I. So angle pi will be this one. This is the thing. So now what we can do? We can go for the Pythagoras theorem and we will write the expression for V. Total V can be written as square root of, that is, this V can be written as square root of VR square plus, in this case, this is VC minus VL whole square. And what we can further do in this, we can substitute the values of VR, that means Vi into R the whole square plus I into XC minus I into XL the whole square. So if you take commonly I outside, you will get V will be is equal to I into square root of R square plus XA minus XL the whole square. And we know that, we know V will be is equal to I into Z commonly. So in this case, Z will be is equal to square root of R square plus XC minus XL the whole square. So this is the final expression for Z in the case of XC greater than XL. And we will go for the case 3 straight away. So case 3, you would have found, you would have know that what is this case? Simply XL will be is equal to XC. Simple thing, right? We know that XL and XC are inverse in nature. A voltage across the inductor will leads the current by 90 degree. In the case of XC, the voltage across the capacitor will lags the current by 90 degree. Then obviously, if these two XL and XC becomes equal, that then obviously we can write this expression as VL will be is equal to VC, and both will cancel each other, and we don't need to go for anything. This will reflects that the whole circuit will act as a resistive circuit, because these two, inductance and capacitance, will be cancelled each other, since the impedance of inductance and impedance of the capacitance, sorry, or not, it is not the impedance value, it is the reactance value. If this one XL is the reactance of the inductor and XC is the reactance of the capacitor, if both are equal, then both the values under AC will be cancelled out. So this will be called as pure resistive circuit. Pure resistive circuit. If it is pure resistive circuit, then what is this one? Obviously, you will get this is VR and this will be I. There is no difference, and it will be the final expression, and we can write it as V will be is equal to VR only, and that is nothing but I into R. And here Z will be is equal to what? Simply R. Simply it will be R. So this is the case 3. You have to understand, it is not a big concept. Since XL is equal to XC, you will get a equal value, so it will be the resistive circuit. So if you are going for impedance triangle, so we will take for the case 1, it will be XL minus XL greater than XC, right? So we have seen this one. See, we have drawn the voltage triangle already. So this is the VR and this will be the VL minus VC, right? So you can convert this voltage triangle to the impedance triangle. How will you do this one? So you have to take this as the R. So we have seen this will be R, and what is this one? This one will be VL minus VC. So we will write this one. See, this is the R and this is nothing but XL minus XC. I'm just writing the reactance values. Now what you can do, you just connect these two phasors, adding these two phasors, we will get, this is the value of Z. And what is this one? This is the value of pi. And you see, now what we can do, we can write cos pi, which is equal to R by Z, right? Cos pi will be is equal to R by Z. And what is the value of Z now? We know this one. See, in an AC quantity, if it is the total Z, then this phasor will be, what is this one? R value plus what is this one? This one will be J of XL minus XC. We have seen this one. See, if you have any doubts in this one, writing the value of Z, we can go for R plus J of XL minus XC. This is the cos pi component and this will be the sin pi component, and this is nothing but it is the 90 degree. So these two will be 90 degree. If you have any doubts, you see my previous lectures to write the expression from the right angle triangle. So this one will be the final impedance value. And you see this one here, this is XL minus XC. So what you do, you just write x1 will be is equal to XL minus XC. You take this, why I am writing this one, this as a 1, since this is the case 1. So commonly you go for RZ is equal to R plus JX. Commonly you write this expression and you can find what is the value of XL and XC from the given values, and you can easily get the value of XL and XC, and you can easily compare XL and XC to know that XL is greater than XC or XL greater than XL smaller than XC. So if you are going for case number 2, let it be a case number 2. What is case number 2? It is nothing but XC is greater than XL, right? So for this one, we have seen this one also. See, you see here. So this is the voltage triangle we have drawn. This is R, and what is this one? This one we can write it as VC minus VL. Here in the impedance case, you can write it as XC minus XL. So anyway, I will write it down. So this is the, so this is R value, this is R, and what is this one? This is nothing but XC minus XL, right? So we will write it down. So this is R and this is nothing but XC minus XL. And if you want to go for EZ, then it is very simple to add these two phasors. Add these two phasors, what you will get? This value will be EZ. And what is this one? This is nothing but pi. And from here, you just try to write what is the cos pi value here. Same, right? What is cos pi? R will be is equal R by Z. And what is Ez here? Ez will be is equal to R plus J of XC minus XL in this case. And what you do, you put X2 will be is equal to XC minus XL. And you write commonly Z is equal to R plus JX. So it is R plus JX is the common term, and you can easily find XL is greater than our XC or XC is greater than our XL from the given values. So this is the impedance triangle that we can draw, and we can derive the expression for impedance values. Now, for the power triangle, it is not necessary to draw the power triangle here. See, if it is a case 1, then there will be the inductive reactance, and if it is the case 2, then there will be some capacitive reactance, higher capacitive reactance will be there. So from that, you can clearly understand in these both cases, that means case 1 and case 2, we will have real power as well as reactive powers. That depends on the XL and XC values. And if it is the case 3, see, in case 3 it is purely resistive circuit. You know that in purely resistive circuit, there will be only real power. Since XL and XC are equal, then inductive and capacitive reactance both get cancelled each other. So there will not be any reactive power available. So we will take up a problem in the next class so that you can easily understand what is the insight that we can apply in the RLC circuit. Thank you. You go through these RLC circuit expressions and you gain knowledge based on these expressions, and we will solve some problems in the next class. Thank you.